Welcome, ladies and gents, to this lecture on waves. Up to this point, we've really described matter in physics and the way in which mass moves. In this topic, we're going to transition away from talking about matter and talk about more of what we call waves. Waves is almost like a way of thinking about energy transfer, because a wave is an oscillation or vibration in which energy moves from one location to another. Now, we can also talk about what's called a wave pulse, which is just a singular disturbance in which energy is transferred from one location to another. But in short, waves tend to be periodic, or they tend to be something that kind of cycle back and forth, and they move energy along. Now, there are two major classifications of waves. We have what's called longitudinal waves and transverse waves. These two categories can classify any type of wave we encounter. Now, a longitudinal wave is a wave in which particles move parallel to the direction of the wave's travel. Meaning, if you think about something being pushed back and forth, that's what we would consider a longitudinal wave. An example of this is when I talk, I create sound. The way in which I create sound is I actually vibrate air molecules back and forth. And as I exert a vibration from my vocal cords, that vibration travels through the air by basically knocking air molecules back and forth. And as those air molecules directly in front of my mouth hit each other back and forth, they then transfer that energy to the molecules closer and closer to my recording device. So when you hear a sound, really all you're listening to is the vibration of air molecules near your eardrum. And that's why sound tends to not travel so easily over very long distances, because it requires a lot of energy to knock those molecules back and forth. Now, longitudinal waves have this kind of pattern in which you can think of these particles being compressed and then released, and then compressed and then released. And what we call these are compressions and rarefactions. So drawing a model for the air molecules in a room, or what we would think of a sound wave to look like, excuse me, we can think of our compressions as zones in which the molecules get really close together, and rarefactions as these empty spaces in between the compressions. And basically what happens in a longitudinal wave is those zones keep on switching. There's compressions, then rarefactions, then compressions, then rarefactions, such that the sound wave is transferred. Now, transverse waves are another type of wave in which particles oscillate perpendicular to the direction of wave travel. An example of a transverse wave would be something like an ocean wave, in which, if you think about it, the wave itself, or the energy, or the particles of the medium, move up and down as the energy is transferred along the direction of the wave's travel, meaning towards the shore, let's say. So if you can picture ocean waves in your head, as you see them coming towards you if you're standing on a beach, the waves themselves seem to create these crests in these lower regions called troughs, in which the particles are moving up and down. But the wave itself comes crashing towards the shore and moves along the ocean towards the shore, and that's the way in which the energy is being transferred. Mechanical waves are another category of waves. It's not as general as transverse and longitudinal. It's a more specific category in which we talk about waves in which waves that require a medium to travel. A mechanical wave is any wave that basically requires a substance to move. Sound is an example of this. If there's no particles to vibrate, there's no way for me to actually create a sound. So if you were to all of a sudden transport yourself to deep space where there's really no particles around you, and you were to somehow survive with taking off your helmet, if you were to start screaming, no one could hear you, not even if they were right next to your mouth, because there's no particles for which that sound can transfer. Unlike this, there are other types of waves that we call electromagnetic waves. these types of waves do not require a medium to travel. For example, light, which is an electromagnetic wave, can travel over vast distances through space. This is what most of our astronomy is based upon. Now, light, as we observe it, we know can travel through space or through long distances without having particles in the way. So, unlike sound, light does not require a substance to travel. Now, going back to the old adage, if a tree falls in a forest and there's no one around to hear it, does it make a sound? Well, physically speaking, yes. Because now we know we can classify sound as a mechanical wave, and sound is a mechanical wave in which a vibration is created. So even if there's no human there to listen to it, there's still a vibration and therefore a sound created when a tree falls in a forest. Last but not least, I'd like to just mention wave diagrams. We're going to get more into these later in this unit, but I'd first like to just describe the basis for the ways in which we can describe a wave. Now, even though this diagram is of what we would consider a transverse wave, meaning the form in which particles will be moving up and down, even though energy might be moving from left to right. Now, the reason why we use these diagrams to draw waves is that they're easier to analyze. And sometimes we might even convert a longitudinal wave that would be drawn by those compressions and then rarefactions into a transverse waveform just to analyze it. It's just easier to look at mathematically. Now, for those of you that are familiar with trigonometry, our wave diagrams are going to take one of two shapes: a sine wave or a cosine wave, or a cosine curve or a sine curve. This one right here would be a sine curve, though for those of you that are a little bit more advanced in trigonometry, you might know that a cosine curve and a sine curve are really one and the same. They just differ by a shift in where you start your wave. Now, let's go into our wave descriptors. Wavelength, just as it sounds, is the length of a wave. Now, more specifically, it's the length of one full cycle. It's where you go from one section into a wave to where it will then repeat itself. So typically we describe this from crest to crest or from trough to trough. Now, a crest is just a peak in a wave, a trough is just a low point in a wave, but our wavelength just describes the length of one full cycle. So there's different ways in which we can measure this wavelength. It just seems to be easiest typically to follow from crest to crest or trough to trough. Even though technically speaking, from this point to this point, these two markers that I have here in red would also be the length of one full wave. Now, wavelength is described by a symbol called lambda. It's a Greek letter, and it's written right here and here. That's just what we're going to use to describe wavelength. Now, realize it's measured in meters because it still is a length. The next descriptor I'd like to go over is what we call amplitude. Amplitude really refers to the energy within a wave, but we draw it on a wave diagram as the maximum distance from equilibrium. So once again, amplitude really measures how much energy you have. The more amplitude you have, the more energy your wave has. In the case of a sound wave, that would be like your volume, right? The more amplitude you have, the louder your wave will be. Okay. The next descriptor I'd like to go over is period. Period is closely related to wavelength in that it also refers to something, a measurement of one full cycle. Now, it's really a measurement of time, though. It's how long it takes a wave to complete one full cycle. So I drew this here in red, and this is once again a measurement of one full wave, and t here would represent the time it takes to do this. So it could also be the time measured from crest to crest. It is closely related to that of our wavelength. Now, last but not least, my last descriptor here is what we call our frequency. Now, frequency is just what you'd think literally what a frequency is, and it's just how often something occurs. Now, the way we describe it in terms of our waves is how many cycles you complete in 1 second. So frequency can be found by taking the inverse of your period, or putting 1 over the time it takes to complete one full cycle will get you your frequency. Now, frequency is measured in units of hertz or Hz. Last but not least, I did add in a formula here for you. It is on your reference table, but there is something that we can use to describe the speed of a wave. The speed of a wave is equal to its frequency times its wavelength. Now, technically speaking, since frequency is 1 over period, you could also think of your speed of your wave as your wavelength over period, which is really just your distance over time, as we've described it in the past. Okay, folks, that concludes our lecture, our introductory lecture here on waves.